see what we have done in the last class as multiplication G, and it's also clear on the notation. So we have H, which is H0 plus H1. This is something that you know the solutions of. You don't know the solutions of these things, but you want to estimate the energies of H and the states. You can do that via perturbation theory if this happens to be small. If you want, you can put a small parameter there. And so 0 means that there is no perturbation, 1 means whatever you have, you can apply it fully. There's a dial, for example, on your perturbation, like you take a hydrogen atom and put it in the magnetic field, and your magnetic field can be changed from 0 to B0. That would correspond in the lambda space going from 0 to 1. So, and if you do that, and if you assume, so these are solutions of H, and these are solutions of H naught. And if you assume that for each n there is an n naught, we can write n as n naught plus small change. In the state. And similarly, if you assume that En can be written as En naught plus En1 plus En2 and so on. If you want to get the lambdas here, then you can show by comparing orders that E1 is N naught H1 and naught E2 is N naught H1 and naught squared over En naught minus En naught sum over and for example, N1 can be written as N naught H1 N naught and N naught okay, right? So this is perturbation theory. You can keep on going. You can calculate E3. You can also calculate N2, N3, E3. But basically, what you have to do is put both of these in this equation, calculate order by order, and just keep on solving the equation. Now, and here we assume something. Here we assume that that the spectrum of H naught, which is let's say 0, 1, 2, and so on and so forth, is non-degenerate. So for each eigenvalue, there is just one eigenstate. Okay. Now, if that's not true, what goes wrong? Suppose that's not true. Right. So there will be some state, there will be two states which will be distinct from each other, but they'll have the same eigenvalue for H, the same energy, and so this will not be defined in that case. But what happens physically? For example, we have a hydrogen atom. A hydrogen atom has states which are given by an element. right? But the energy only depends on n. So for each value of n, there are n squared states which are degenerate. Now what happens? So if you take a hydrogen atom, put it in a magnetic field, suddenly all of the energies become infinite. Becomes a black hole, everything goes in. Is that what happens? I mean, this tells you that as soon as En and Em are going to be equal, this is going to diverge. Right? It's not going to remain small, and so basically it should become a black hole. That's absurd. It's not going to what's going to happen. In fact, when you put the hydrogen atom in the magnetic field and you look at the spectrum is going to be about the same. It's not going to be much different if the magnetic field is not very strong. And so, you will see something, you will see a spectrum which will be very similar to the spectrum for H0. So then, it must mean that whatever mathematical framework we have developed to talk about perturbation, it just doesn't deal with degenerate perturbation. So you have to think of something else, right? Does it make sense? So what will happen? So for example, if you look at the situation like this. So suppose this is the E-axis, this is the ground state, the first excited state, blah blah blah. So we have all this set of states. And for a given one, let's say this one, this state, this is degenerate. These are the eigenvalues. So E0, E1, E2, blah blah blah. And so En, let's say this is degenerate. And let's suppose there are two states that corresponds to En. Okay? So you apply perturbation, what will happen? Well, all of these energies are going to shift a little bit, right? Something like this. And so the new spectrum will form. That's what's going to happen, right? Maybe it will also happen that sort of perturbation is going to lift this degeneracy. What it's going to, and in fact, that's what we want our perturbations to do. One of the reasons we apply perturbation is to break the degeneracy. For example, if we have n squared states for each NLM, we want to see whether there are n squared states or not. And if you just look at the spectrum for the hydrogen atom, it doesn't really show you, it doesn't really tell you that there are different n states for each value of the energy. There are n squared different states. It doesn't show you unless you look very, very closely. We'll talk about that. But let's suppose that we do put that atom in the magnetic field and we want to lift this degeneracy. So what will happen? For example, if we're talking about this two-state system and we apply a perturbation that lifts the degeneracy, what will you get? You'll get something like this, right? So you will have one energy corresponding to two states, but as soon as you apply the perturbation, and this axis is lambda, so this is 0 and this is 1. Right? We can apply lambda, and we can keep writing lambda as 0.5, then we get something like this. So this state n will go to something like n plus and n minus.
So n plus and n minus have different energies?
Yes. Now they have and these two states don't have different energies when lambda is 0. But when lambda is finite, when you turn on the perturbation, then these two have different energy. These are the energies that I'm talking. So here on this axis, on this line, when lambda is 0, the energies are all distinct except corresponding to this energy there are two states. So when you turn lambda on this axis, again, these energies are going to be shifted by a little bit, but the most important thing that happens here is that there are two states that correspond to this energy, but now they are distinct. Now they have different energies by a small amount. By a small amount, but nonetheless different energies.
That's like when we put the spin half particle
Yeah, exactly like that, right? So if you take an electron and if you talk about the free particle energy, it's degenerate. It doesn't take into account the spin of the electron, let's say. But if you put a magnetic field, right, then spin up and spin down have different energies by a very small amount.
So the final energy will be the initial energy plus minus the spin.
Final energy. I don't know what you mean by final energy. So this is, let's say this was the earlier energy. So this is change in the energy. This is E1, and this is the change in the energy for this state. That's also E1. You can call this E1 plus, E1 minus.
So if it is an electron, before it's been put into a magnetic field, what would be its energy? And afterwards, how would it be?
Whatever energy you've given it. If it's a free electron, then you can give it any energy that you want. Right?
But after putting it into field, it would be the that amount minus the.
Yeah, that amount minus or plus
Yes,
mu d. Right. Right? Anyhow, so now think of starting from this point. Right? Suppose you have perturbation on, and you sort of dial back the perturbation and take it from 1 to 0. What will happen? You have these two states, and they will go back into the two states here. Right? By the way, there are two states here, right? And so this is a degenerate eigenspace. Degenerate. So the whole so the whole space spanned by the two vectors is degenerate. What two vectors I'm talking about? So I'm talking about, let's say that NA is En naught, and then there is another state, N naught B, which also has the same energy. Right? And so the space spanned by these two states is going to be the degenerate space here. So when you take these two states and sort of take them back into this space here, they will go into a linear combination, NA and B. Right? If we had known that combination to begin with, we would be in so-called good state, we would be able to do perturbation theory just regularly. Right? The problem is that this is sort of a singular, whatever, some undefinedness or some singularity that's happening because you don't know the good combination of states that you really need. So when you turn these off gradually, they gradually go into a combination of states. Had you known that combination of NA and NB to begin with, you wouldn't have this problem. So our job is to just find out of those infinite number of states, the good combinations of these two states, which is just going to be two states. Does that make sense? Yes.
So I'm confused about lambda. When we are doing it to the first order, we consider lambda to be very small.
You can take lambda to be as small as you want or as large as you want, right?
Then
it just has to be that the whole thing, this whole thing has to be small. Right? You can, if you are sort of, just take it from 0 to 10 to the power minus 3. Who cares?
so we can scale it up to whatever.
Whatever you want. So then it will lie between 0 to 10 to the power minus 3. There. Instead of between 0 to 1. Right? But then you can renormalize it, and whatever number was 10 to the minus 3, you can make it 1. Anyhow, so let's start with this and then we'll generalize this. So let's suppose that there are these two states corresponding to a given energy state here, and we have a Hamiltonian H1 that breaks this degeneracy, and we want to solve for the first order corrections to the state and the first order corrections to the energy. So let's write these states that we want as alpha of n is 0 plus beta and n is 0 plus, and then we can So you have these two combinations. And we do usual thing, you write E as En0 plus En1 plus En2. These are orders. They have to be successfully
So for constants in NA and N plus.
So the two states that we have chosen here to act as the basis of that degenerate eigenspace are NA and NB. This could be any two states which are orthogonal to each other. Okay? You can normalize them. But we want actually these two states, which we're calling good states. Our job is to find these alphas and betas.
So why would they be a combination of NA?
Because they will, so when we turn this off, this goes back into the same eigenspace. That eigenspace is being spanned by these two. So there must be a linear combination of these two. Right? And similarly, N is going to be N0 plus N1. Are there any questions about the notation? Right? In the last class I was using, so this is Shankar's notation, and I think reference uses this. Psi n is equal, or psi n is equal, psi n of x is equal to psi n naught of x plus psi n1 of x. Right? Same thing. Same thing. Any questions? So, if you there's lambda square. Oh, I don't forget this. Anyway, so if you plug these equations back into those equations over there, you can show, and we have done this, so I'm not going to it, that that the first order result is h naught n1 plus h1 n0 is equal to e n0 n1 plus e n1 n1. Right? You guys know where this comes from, right?
Yes.
Okay. Now, dot with n a naught from the left. Or if you want, you can. And then this will become n a naught h naught n1 plus n a naught h1 n0 is equal to e n naught n a naught n1 plus e n1 n a naught right? By the way, what is this n0? What is this n0? This was supposed to be degenerate. Plus and minus. This is one of these things. This could be the plus or minus, whichever one you want. Okay? It could be NA naught, NB naught, or any linear combination. Okay? So this could be any linear combination. What is this thing? What is this equal to? NA naught, N1. Why? Why are they common? What? So these should be orthogonal. In general, they are, but we haven't shown that. But you can see that if you apply this here, what you get is E N naught, N A naught, and 1, which is the same as this. This will cancel with this. You don't have to have it with you. But on the other hand, what is this thing equal to? Alpha. This thing is equal to alpha. Okay, so this thing is NA naught H1, and for this we can write alpha NA naught plus beta and B naught equal to alpha E1.
So why have you expanded n in n naught n1 and
Okay.
so what do you mean when you have expanded n in n naught n1 and the second one?
Okay.
So state n is the state again?
I don't know what you mean by state n is state n. It has the eigenvalue En.
Unperturbed state n.
This is the unperturbed state n. And we can choose this to be any of these, or the linear combination, any linear combination. And so a general linear combination is written here.
So then what is n1?
N1 is the first order correction to the state. This state is basically the same as this, but this is the first order correction into this. Right? Okay, and so by the way, these matrix elements, these are supposed to be known. So you have A, H1, B, let's call it omega AB. These things are known. Okay? These are not real numbers necessarily, but they are known. In fact, this is a real number. This is omega AA. So you can write this equation like this: alpha omega AA plus beta omega AB is equal to alpha E1. Now, had you started with dotting with N naught B, you would have gotten another equation. You would have gotten alpha omega BA plus beta omega BB is equal to beta E1. Now you can solve these equations. If you know all the matrix elements, right? There are only two unknowns, alpha and beta, and you can solve in terms of those, and you can show that if you try to solve them, this is homework now, that you can construct this equation. The equation that you construct is E1 squared minus E1 BE plus AA plus omega AA omega BB minus omega AB mod squared is equal to 0. And this is a second order equation. This is the quadratic equation in E1, and the solution is E1 is equal to 1/2 omega BB plus omega AA plus minus omega AA minus omega BB squared plus 4 omega AB squared. And since this is plus minus, we have plus minus. And we have two roots. Right? And so, to first order, the energy En is just En naught plus E1 or minus E1. now the degeneracy is lifted. Now, if you look here, had alpha been zero, so these are the good states. These are the good states. If you somehow happen to choose the good state itself, I mean, if these two are good states, then this alpha should be 0 here and beta minus should be 0 here, right? So if alpha is 0, what does that lead to? That leads to that omega WAB is 0. So the good states are the states that diagonalize H1. So you don't have to actually go ahead and do all of this. If you can just guess somehow that these two states that will diagonalize H1, then you can just calculate E1 directly. And in that case, you can show that E1 plus is just 1/2, just by looking at this, is 1/2 WAA plus WBB, and let's assume that WAA is greater than WBB, right? Then by looking at this, you will get plus WAA minus WBB, and that will 1/2, and that will just be WAA. So if alpha is 0, all that you have to do is calculate the matrix elements of A, just like you did in that case over there, and that will give you the right result. So the good states are the states that diagonalize H1. Questions? Comments? Complaints? Remarks? Nothing? No. Cool. That's it. Homework. Show that N0 plus is perpendicular to N0 minus. Okay, we have to show that these two states that you have calculated are perpendicular to each other. How can you calculate the states? Once you have E1, put it back in there, calculate alpha and beta, and once you have alpha and beta, you will have these states. Show that these are perpendicular to each other. Okay? Any questions? Okay, let's try to generalize the whole thing. Now this state need not be doubly degenerate, it could be triply degenerate, quadruply degenerate, it could be n-fold degenerate. What would you do then? Well, what have you done here? Look at these two equations. The answer is here. You can write the whole system like this: WAH, WAB, WBA, WBB, alpha beta is equal to E1, right? What are these things? What are these things? Where do these come from? They are matrix elements of H1 in the degenerate eigenspace, right? So you have a basis for the degenerate eigenspace. All of those states are eigenstates of H0, but they have the same value for the energy, right? But these matrix elements are calculated. So you calculate them. What are these things? These are just eigenvectors of this matrix. And these are just eigenvalues of this matrix. If you had been lucky enough to recognize the right states to begin with, these would be 0, and these would be diagonal, and these would be 0, 1, and non-zero, the eigenstates. And you would be in the good states. But if you can't do that, right, then just calculate these things. H1, J, so Wij, make this matrix and solve the eigenvalue problem. That's it. Right? Or construct a basis in which, in the degenerate eigensubspace that diagonalizes H1, whichever one you like. And I'll also give you a theorem that will help you do that. We'll discuss that theorem later. But before that, let me just solve an example, and mostly you will be doing the calculations in the homework, but I will sort of put you on your way just to make sure that you understand what we mean by diagonalizing that matrix. So for example, you can solve this problem, B, X, Y, Z. This is a three-dimensional infinite potential well, right? Three-dimensional infinite potential well means that this thing is 0, potential is 0, if X is between 0 and A, Y is between 0 and B, A, well, we can't have B, otherwise not be degenerate. 0, A, infinite otherwise. Right? So this is three-dimensional infinite potential well. What do the states look like? What do the states look like? 2 over A, 3 by 2 sine n pi x over A, sine n pi y over A, sine n pi z over A, because the differential equation just decouples and there were just three differential equations that we have to solve exactly accordingly to what we had done here. Except since these n's are independent, maybe you should put nx, ny, and nz. Okay? And so this thing is nx, ny, and z. Or maybe you should call them n1, n2, n3. Okay? What is the ground state energy? Right, so energy of the nth state is pi squared h10 squared over 2ma squared, and instead of n squared you have nx squared plus ny squared plus nz squared. Right? And so the ground state energy E0 is just pi squared h10 squared over 2ma squared, and this would be 0? Would this be 0? For the ground state. So 3. So n, the smallest value that n can have is 1, right? And so nx would be 1, and y would be 1, and nz would be 1, and so this is the ground state energy. But now if you look at the first excited state, any two of these could be 1, and the next one could be 2. And so you have three states, psi 1, 1, 2, and psi 1, 2, 1, and psi 2, 1, 1, which are degenerate. Right? So this thing was something like, so this box was something like this, right? Now you introduce a perturbation. You introduce a perturbation where x, and this is x, and somehow, I don't make the picture right, but you introduce a perturbation that this part of the box, maybe if I try to make it right, let's do this. And then this part, this, yes, this part here, this part of the box, you make this a slightly higher potential V0. Okay, so this one, I can write it down. So H1 is equal to V0, right? If 0 is less than x less than a by 2, 0 is less than y less than a by 2, right? And 0 otherwise. So in this part, you have changed the potential by a small amount. So what happens to the ground state? Well, the ground state is not degenerate. And so, all that you have to do is calculate for the ground state, the first order change in the energy is just going to be 0, which is the ground state, H1, 0. And if you calculate that, that comes out to be a quarter of V0, because this is just the quarter of the whole thing. Okay, this region is just the quarter of the whole thing. And so, the first order change you got is 0. But if you come to now to calculate the first order change in the first excited state, then you can't just use that formula. What you have to do is now first calculate WAA, and you can show that that's also equal to V0 over 4, and so is WBB and WCC. Now this is, all of this is homework. So you go ahead and show that. You also, this part, everything on this board is homework. You show this, you show that, and you also show that WAB is equal to WBA. They are just complex conjugates of each other. This is 0. And WBC is equal to WCB, which is equal to 16 over 9 pi squared V0. And so if you calculate, if you construct the W matrix, it is equal to V0 over 4, 1, 1, 1, and 0 and 0, and 0 and 0, and kappa, where kappa is 8 over 3 pi squared. And so if you calculate the characteristic equation, it turns out that W1 is 1, W2 is 1 plus kappa, and W3 is 1 minus kappa. So these are the eigenvalues of this matrix. And hence, there are changes in the energy to first order. So the first order, right, this is n is equal to 1, so first excited state, right, lambda, this can be written as E01 plus 0.25 lambda V0, E01 plus 0.43 lambda V0, and E01 plus 0.07. And if you sort of make this diagram, this was E1, which was degenerate, and now it sort of goes like this. So this here is lambda, 0, 1. Questions? And now you want to maybe calculate the good states. How would you do them? How would you do that? Well, you already, yes, you already know the eigenvalues. All you have to do is, so you have W, alpha, beta, gamma is equal to some eigenstate, let's say W1, alpha, beta, gamma. Solve this, that will give you the first good state. Then do it for W2, that will give you the second good state. Do it for W3, that will give you the second, third good state. And if you do that homework, you can show that N naught N naught is this should be N. Okay. N to first order, that's what I should say. N to first order is psi of A. I'm calling this, I think I'm calling this A. One, one, two is A. Yes. So this is psi of A, psi of B, psi of C, psi C. So this is psi A, psi B, plus psi C, 1 over square root of 2, and psi B minus psi C. So, I should say 1. Right? Okay. Let's try and calculate, and now I'm telling you the theorem that I was mentioning earlier. Let's try and calculate the relativistic correction to the hydrogen atom. So before we do that, let's see. So in that case, H1 is equal to minus P4 over 8m cubed C squared. Do you understand what this is? So we've been using that the kinetic energy, that's called P, it is equal to P squared over 2m. Right? That's what you use. But this is just a classical approximation to the relativistic result. So the first order correction to this result is this. Homework, prove it. How would you do this? T is equal to E minus mc squared, where E is P squared C squared plus m squared C4 square root minus mc squared. So open this up, take mc squared, let's say, common outside, and so this will become P squared over m squared C squared minus mc squared, 1/2. Open this up and show that the first order term that you get, so show that this is equal to P squared over 2m minus 1 over 8 P4 over m cubed C squared, like this. Right? Okay. So now our job is to calculate the shift in the energies of the electron, in the energies of the hydrogen atom, spectrum of the hydrogen atom, due to this perturbation. Okay? So again, what? You will have to do what? You will have to calculate this in we'll have to calculate n prime, l prime, m prime, h1, n, l, m. For each n, you will get n squared states, and so you will get n squared into n squared matrix. We'll have to diagonalize. right? Or you can do something else. What else can you do? Let's try to figure that out. Guys, questions? No? आप पूछ रहे हैं कि परटर्बेशन है क्या? इस बात का कोई मतलब नहीं है जो आप पूछ रहे हैं। अगेन इसका कोई मतलब नहीं है जो आप पूछ रहे हैं। एक ऑपरेटर है, उसको किसी भी स्टेट में अप्लाई कर सकते हैं। आप ये पूछ रही हैं, अगर आपको ये क्लियर है कि हमने ये क्या किया, then you wouldn't ask that question, right? ये क्या किया हमने यहाँ पर जब H1 दिया था तो किस पर अप्लाई किया? कौन सी स्टेट पे? हर स्टेट पे अप्लाई किया। लेकिन हमने हर स्टेट वगैरह पर अप्लाई करने हमने बेसिकली ये मैट्रिसेस चाहिए। हमने उसको डिजनरेट स्पेस में जो भी डिजनरेट स्पेस थी, for a given n you have n squared states. For 2 you have 4 states, for 3 you have 9 states, for 4 you have 16 states, and before you have 16 states that have the same energy, right? So you have to construct a 16 by 16 matrix and then diagonalize it. That's what you have to do. So you're not applying it on any state. You have a perturbation, you have an H1, you have to calculate this matrix elements. Or you can do something else. What else you can do? That's what I'm going to talk about. Let's suppose that you have an operator that commutes with H1 and also commutes with H0. Right? Okay. Now let's look at this. And we are talking about the eigenstates of A. Right? So, for example, these two are going to have the same eigenstates, right? So, for example, the eigenstates that I use and A and B, right? If I put this H1 in there, so these are also eigenstates of A, right? Right? Or you can make a linear combination of these to make them eigenstates of A. You understand? We've talked about this. Right? When they commute, you can always choose a set of common eigenstates that forms a basis. Right? So what is this equal to? Why 0? Yes, excellent. Because the operator is 0. Right? So, अब देखेंगे क्या है इसके साथ जब आप A के ऊपर अप्लाई करेंगे, अच्छा अगर A B इसकी eigenstates है, so this will be equal to B and 0 B, and now you understand what this B means. A n0 A and so n0 A. अब अगर आप ये अप्लाई करेंगे, so then this becomes A minus B n A naught H1 and B naught is equal to 0. So either this is equal to 0 or this is equal to 0. So if A is non-degenerate in this eigen subspace, which means that for these two it has different eigenvalues, then this can't be 0, and hence this is 0, and that is the condition for the good states. So if you can find an operator that commutes with both H1 and H0 and happens to be non-degenerate in this eigen subspace, then the eigenstates of A are the good states. Does that make sense? Guys? Jia? दोबारा से? कहाँ से दोबारा से?
ये जो आपने good states वाली जो बात करी है,
Good states क्या होती है बेटा?
we use to extend to their
Diagonalize कर देते हैं, right? So you want these matrix elements when A and B are different to be 0. हमने ये भी प्रूव किया कि अगर ये A इन दोनों से कम्यूट करता हो, जिसकी वजह से इनके दरमियान एक कॉमन आइडेंटिटी होगी, राइट? और ये खुद नॉन डिजनरेट हो, खुद डिजनरेट ना हो इसका सो इस केस में ये चीज जीरो नहीं हो सकती, ये चीज जीरो होगी, जिसका मतलब है कि इसकी जो आइगन स्टेट्स हैं उस डिजनरेट आइगन सबस्पेस में दे हैपन टू बी इक्वल स्टेट्स। वो इसलिए जीरो नहीं है कि ये नॉन डिजनरेट है, ए और बी सेम नहीं हो सकते। अगर तो ये डिजनरेट है फिर तो हमें कुछ भी नहीं मिला, पहले भी डिजनरेट था डिजनरेट, वो तो आप वन ले लेते। नहीं निकालेंगे नहीं, आपको देखना पड़ेगा आपको ऑपरेटर मिलता है या नहीं मिलता। जैसे भी हम ये जब सॉल्व करेंगे ये वाला प्रॉब्लम तो आप देखेंगे कि कैसे मिलेगा। You just have to see, ठीक है। अच्छा अब बताइए ये समझ आ गया। अच्छा अब वापस आ जाएगा। अब ये बहुत लंबा काम है फॉर ईच एन, और जैसे जैसे एन बढ़ता जाएगा ये मैट्रिक्स बहुत बड़ा होता जाएगा, ठीक है। लेकिन टर्न्स आउट दीज आर गुड स्टेट्स। कैसे बताओ? अगर ए डिजेनरेट है तो सब कुछ फायदा नहीं, अगर ए नॉन डिजेनरेट है तो फिर उसका फायदा, या जिन अगर वो पूरी तरह से डिजेनरेसी नहीं भी लिफ्ट करता, कुछ डिजेनरेसी लिफ्ट कर देता है तब वो कुछ फायदा नहीं है। अगर वो मुकम्मल तौर पर डिजेनरेसी लिफ्ट कर देता है तो उसकी सारी आइगन स्टेट्स जो बेसिस बनाएंगी फिर उस आइगन सब स्पेस में दे विल जस्ट बी गुड स्टेट्स। नहीं समझ आ रहा? हो सकता है कि तीन और उसकी जो आइगन वैल्यूज है वो लेट्स सपोज कि इनिशियली आपके पास 10 फोल्ड डिजेनरेसी है और ए जो है वो 4 या 5 डिफरेंट आइगन वैल्यूज देता है, 10 नहीं देता, तो फिर उसमें कुछ डिजेनरेसी लिफ्ट करनी है बाकी नहीं करनी। यानी कि वो उस आइगन सबस्पेस को मजीद छोटी छोटी आइगन सबस्पेस में तकसीम कर देगा और उनमें से हर एक आइगन स्पेस को अलग कर देगा, लेकिन पूरी तरह से डिजेनरेसी को लिफ्ट नहीं करेगा, ठीक है। हाँ जी, क्वेश्चंस गाइस, एनी मोर क्वेश्चंस? उसको पैसे देके आते हैं क्वेश्चन लेने के लिए ताकि और किसी को पूछना ना पड़े। अच्छा, anyhow, so these are good states. Why? जल्दी का टाइम नहीं है आज just have to go through all of this. ये P4 है ना, और इनिशियल और जो H नॉट है वो क्या है? P स्क्वायर है। ये दोनों कम्यूट करते हैं L स्क्वायर से भी और LZ से भी, और ये L स्क्वायर और LZ की आइगन वैल्यूज है, और ये नॉन डिजेनरेट है, so they are good states, ठीक है। सो आपको कुछ भी करने की जरूरत नहीं है, आप हर NLM के लिए इस चीज को कैलकुलेट कर लें एंड दैट विल गिव यू रिजल्ट, ठीक है, क्योंकि डायगोनल एलिमेंट फ्री है। सो इन दैट केस दिस विल बिकम E1 will become minus P4 over 8m cubed C4, और आप इसको कैसे कैलकुलेट कर रहे हैं? इसको कैसे कैलकुलेट कर रहे हैं? P squared on side is just 2m E minus V on side, right? ठीक है, तो आप इसको ऐसे लिख सकते हैं minus 1 over 8 m cubed C4 NLM P squared NLM, and this basically becomes minus 1 over 2m, ये 2m इधर से आगे कुछ खत्म कर देगा और कुछ आपके पास रह जाएगा। If you have questions ask. E minus b squared इसके इक्वल होगा। ये हम एवरेज दे रहे हैं NLL, right? And so this will be equal to minus 1 over 2mc squared. ये हो जाएगा e squared minus 2e v plus b squared, और अब v क्या है? v है माइनस के बी ओवर हाफ, एंड सो बेसिकली इसकी जगह आप लिख सकते हैं प्लस अब ये हम n कैलकुलेट कर रहे हैं, ई एन, सो ये हो जाएगा ई एन, क्वेश्चन है कैसे जो बता रहे, ई एन स्क्वायर प्लस 2en ई स्क्वायर के 1 ओवर आर की एक्सपेक्टेशन वैल्यू और के स्क्वायर ई फोर 1 ओवर आर स्क्वायर के। यहाँ पर तो ये होमवर्क है कि यहाँ से यहाँ कैसे जाएंगे आप ये देख लें। ए जो है ना वो है एच का स्क्वायर, हमारे यूनिट्स में ए जो है वो एच का स्क्वायर ओवर एम ई फोर, और ई वन जो है ई वन जो है वो है माइनस एम ई फोर। ये फर्स्ट एक्सरसाइज स्टेट क्या रहती है, अनपर्टर्ब्ड ओवर 2h का स्क्वायर, इन दोनों को यूज करके, और ई एन जो है वो है ई वन का मैग्नीट्यूड माइनस ओवर एन स्क्वायर। ये सब यूज करेंगे, यू कैन रिड्यूस इट टू दिस, और इसका रिजल्ट आपको पता है या आप कैलकुलेट कर सकते हैं, राइट? जी क्वेश्चंस? नहीं लास्ट क्लास नहीं है, लेकिन आई वांट टू फिनिश द डिटरमिनेंट परफॉर्मेशन थ्योरी। नेक्स्ट क्लास विल बी इंशाल्लाह लास्ट एंड टाइम डिपेंडेंट परफॉर्मेशन थ्योरी, but we might have to go for more than 2 classes for ED. Let's see how much we can cover in today's class. हाँ जी, समझ आ रही है क्या हो रहा है, राइट? अच्छा, अब जो 1 ओवर आर स्क्वायर है, 1 ओवर आर की जो एवरेज वैल्यू है, ये भी होमवर्क है, ये आपने कैलकुलेट करके लानी है। अगर टाइम हुआ तो मैं आपको फाइनमेंट एलिमेंट थ्योरम से इंट्रोड्यूस करवा दूंगा, वो आपको ये कैलकुलेट करवा देगा। L plus a half L cube। So अगर आप ये वैल्यूज यहाँ पे पुट कर दें, so homework you can show that en1 is minus en squared over 2mc squared 4n over L plus a half minus 3। यहाँ पे पहले किया हुआ, ठीक है, यहाँ पे पहले किया हुआ है, और ये सारा कुछ किया हुआ है, और फिर ये भी आपने किए हुए हैं। आई एम जस्ट रिवाइजिंग दिस प्रोग्राम so that if you have any questions you can ask now, ठीक है? Guys, questions? Right? तो दूसरी जो हम हाइड्रोजन के लिए करेक्शन कैलकुलेट करना चाहते हैं वो कहलाती है, क्या कहलाती है? एलएस करते हैं। वेरी गुड, तुमने नादिया अच्छे रखते बारे में एलएस में है। हाँ
बाकी का तो लिखा था वो कम है।
मुझे क्या पता क्या लिखा है? ये वाला ये लिख कर आते लोग देखो वो तो बड़े अल्फाज परेशान हो गए, कहाँ हो गया? अच्छा जी, अगर आपके पास मैग्नेटिक फील्ड हो और आपके पास कोई मैग्नेटिक मोमेंट हो तो वो कपल करता है and the energy is minus mu dot b, ठीक है? If b is small, right, then we can treat this as a perturbation. अगर आप इलेक्ट्रॉन को देखें तो वो चक्कर लगा रहा होता है न्यूक्लियस के ऊपर। अगर आप इलेक्ट्रॉन के फ्रेम में हो तो न्यूक्लियस उसके लिए चक्कर लगा रहा है। जब न्यूक्लियस के चक्कर लगा रहा है that generates a current. That current generates a magnetic field. So electron feels a magnetic field in its frame. You can show that, and this is homework, that B is E over 4 pi epsilon naught. 4 pi epsilon naught, as I said, is K 1 over mc squared L cube L over R cube. And after that? आप जो मर्जी फ्रेम यूज कर लें, as long as the frame is inertial. असल क्वेश्चन ये है कि जो इलेक्ट्रॉन का फ्रेम है वो inertial, ये बात है। So there is a cheating here. नहीं, मतलब कि अगर आप प्रोटॉन के फ्रेम में हैं और प्रोटॉन मूव नहीं कर रहा, राइट, तो वो inertial फ्रेम है। लेकिन अगर आप वहां से इलेक्ट्रॉन के फ्रेम में चले जाते हैं, that jump is not quotient because electron is not an inertial frame, ठीक है? लेकिन जब आप legitimate calculation करते हैं, turns out you have to write it down. So hand waving के तौर पर ये argument दिया जा सकता है।
लेकिन हमें सारा फॉर्मूला एक ही पे में रखना है।
नहीं, वो जरूरी नहीं है, ये जरूरी नहीं है। किसने कहा? आप जिन फ्रेम से मर्जी इस्तेमाल करें, आपकी फिजिक्स जो है फ्रेम इनवेरिएंट है। So frame is like a gauge for you. You can use any gauge that suits you. जैसे आप ये कहें कि अगर आपके पास स्फेरिकली सिमेट्रिक सिस्टम है, अभी तो आपने डेल जो लिखा था वो है रेक्टेंगुलर कोऑर्डिनेट्स में लिखा था, अब आप उसको ले गए हैं स्फेरिकली सिमेट्रिक स्फेरिकल कोऑर्डिनेट्स में, आपको एक फ्रेम इस्तेमाल करना चाहिए। एक किताब लिखी है, आप एक फ्रेम इस्तेमाल करें। आप क्या हर वक्त एक फ्रेम से दूसरे फ्रेम, दूसरे फ्रेम से तीसरे फ्रेम जाते हैं, आपको एक फ्रेम पसंद।
इलेक्ट्रॉन के फ्रेम में पहले हम एक फील्ड कहते हैं, इलेक्ट्रॉनिक फील्ड में प्रोटॉन।
आपने इलेक्ट्रॉन की फील्ड निकालनी है ना, तो आप इलेक्ट्रॉन के फील्ड फ्रेम में जाएं और देखें कि वो कौन सी फील्ड एक्सपीरियंस कर रहा है।
करंट तो नहीं दे सकते इलेक्ट्रॉन के फ्रेम में, इलेक्ट्रॉन स्टेशनरी है,
दोनों का करंट तो सेम है, दोनों का करंट तो सेम है एक दूसरे के लिए।
लेकिन इलेक्ट्रॉन के फ्रेम में तो इलेक्ट्रॉन स्टेशनरी है ना,
ठीक है,
तो अब उसके हम
तो फिर प्रोटॉन का करंट है, तो प्रोटॉन का करंट इलेक्ट्रॉन की पोजीशन पे एक मैग्नेटिक फील्ड जनरेट करेगा और इलेक्ट्रॉन का एक म्यू है, वो म्यू उस फील्ड से कपल करेगा। दैट्स इट। अब इसमें क्या मसला है?
इलेक्ट्रॉन का करंट तो
नहीं, इलेक्ट्रॉन का करंट ना यूज करें, अगरचे दोनों का करंट सेम है लेकिन ना यूज करें, आपको नहीं पसंद है ना यूज करें। इलेक्ट्रॉन के फ्रेम में जाएं, उसके फ्रेम में न्यूट्रॉन प्रोटॉन मूव कर रहे हैं, वो जो प्रोटॉन मूव कर रहा है करंट जनरेट कर रहा है और वो करंट इलेक्ट्रॉन की पोजीशन पे मैग्नेटिक फील्ड जनरेट कर रहा है, वो मैग्नेटिक फील्ड कपल कर रही है म्यू से। म्यू किसका? इलेक्ट्रॉन का। और खत्म, बस। ठीक,
तो जो एल है वो इलेक्ट्रॉन का,
एल इलेक्ट्रॉन। ये एक जेन्युइन क्वेश्चन है, तो आप पूछो, ये बात ठीक है। जब आप पूरी कैलकुलेशन करते हैं, टर्न्स आउट कि जो इलेक्ट्रॉन का क्योंकि बेसिकली दोनों एक दूसरे के जो चक्कर लगा रहे हैं उनका रेडियस सेम है ना, उस वजह से ये L जो है वो इलेक्ट्रॉन का आप लिख सकते हैं। इसलिए कि वो एक इनर्शियल फ्रेम नहीं, वो एक्सेलरेटिंग फ्रेम। इलेक्ट्रॉन एक्सेलरेटिंग फ्रेम नहीं, बिल्कुल घूम रहे हैं। तो उस फ्रेम में आपको फोर्स फील होगी ना, आप दीवार के साथ लगे होंगे ना, जब दीवार घूमेगी दीवार, आपको पता होगा कि ये इनर्शियल फ्रेम नहीं है, ठीक है। बेसिकली ये बहुत सी हैंड वेविंग के साथ ये हम निकालते हैं, लेकिन अगर आप हैंड वेविंग के बगैर भी निकालें ये एक्सप्रेशन तो यही निकलता है। इसलिए हम ज़्यादा चीज़ों को बाहर नहीं करते, लिख लेते हैं। या आप यूँ समझें कि दिस इज द मैग्नेटिक फील्ड दैट यू कैन कैलकुलेट, दैट द इलेक्ट्रॉन फील्ड्स, where this L is the angular momentum of the electron, ठीक है। और जो mu है, mu is gamma s, where s is the spin of the electron, this is the gyromagnetic ratio, and if you calculate, this comes out to be E over 2, Q over 2m, so basically E over 2m, and so यहाँ पर भी एक 2 का फर्क आता है, यहाँ पर भी एक 2 का फर्क आता है, दोनों एक दूसरे को बेसिकली कैंसिल कर देते हैं। ये आप कैलकुलेशन अगर पूरी करें तो ये भी गलत है, ये भी गलत है, लेकिन फाइनल रिजल्ट जो मैं लिखूंगा H1 के लिए वो ठीक है। सो इस सब को भूल जाए अगर आप, तो आप सिर्फ ये देखें कि जो स्पिन ऑर्बिट कपलिंग है उसकी वजह से जो H1 है या H है वो E² over 8 pi epsilon naught 1 over mc² 1 over mr³ s dot n, ठीक है बस। तो ये स्पिन ऑर्बिट कपलिंग। आप बताएं कि इसको कैसे सॉल्व करेंगे, ठीक है। सो L डॉट S को आप लिख सकते हैं 1/2 J² minus L² minus S², right? And so the eigenstates of this operator are J1, J, Jz, J1, J2, right? Where J is N plus S, J is N plus S, ठीक है। तो हमें ये पता है कि ये स्केलिंग स्टेट्स है और यही गुड स्टेट्स भी है। क्यों ये गुड स्टेट्स हैं तो बता सकते हैं, ये गुड स्टेट्स हैं। अब दोबारा जब आपने H1 कैलकुलेट करना है तो हाइड्रोजन आइटम जो है वो n² टाइम डिजेनरेट है फॉर ईच स्टेट। सो आपको गुड स्टेट चाहिए या फिर आपको कोई W कैलकुलेट करके उसको डायगोनलाइज करना पड़ेगा, वही मसला है। Turns out that these are good states. Why? Because they diagonalize H1. And these are eigenstates of S dot L. So luckily, just to begin with, you know what the eigenstates of S dot L are. Since they diagonalize H1, they are good states. ठीक है। और again homework, जब आप इनको ये इसकी eigenstates क्या होंगी इनमें S dot L की, वो होंगी J into J plus 1 जो possible values है J की, minus L into L plus 1 minus 3/4 S into S plus 1 H cut squared and then this is factor of 2 और यहाँ पर R cube है, या असल R cube होना चाहिए, R cube है और इसकी आपको चाहिए इन स्टेट्स में इसकी क्या से कहते हैं एक्सपेक्टेशन वैल्यू चाहिए। दैट टर्न्स आउट टू बी L into L plus 1 L into L plus a half L plus 1 N cube A cube, ठीक है। और साथ ये फैक्टर्स आ जाएंगे 1 over mc² and this one ke², 4 pi epsilon naught c²। अब ये जो दोनों हमने एक पहले निकाली थी, एक हमने पहले कहाँ निकाली, वो ये भी सम एनर्जी ओवर mc स्क्वायर्ड है, सम एनर्जी ओवर mc स्क्वायर्ड, सो दे आर द सेम ऑर्डर। तो जब आप इन दोनों को ऐड करते हैं तो ये सेम ऑर्डर का इफेक्ट है, और इसको हम फाइन स्ट्रक्चर कहते हैं हाइड्रोजन एटम। इन दोनों को अगर आप ऐड करें तो दिस कम्स आउट टू बी En स्क्वायर्ड ओवर 2mc स्क्वायर्ड। ये mc स्क्वायर्ड है क्या ना, 3 माइनस n 4n ओवर j प्लस हाफ। ये सारा आपने पहले कैलकुलेट किया होगा, इसलिए मैं इसके अलजेब्रिक स्टेप्स नहीं कर रहा। अगर आपको ये पता हो और आपको ये पता हो, इन दोनों को आप ऐड करें, क्लेम इज दैट द आंसर इज दिस। ठीक है, अब ये J में L भी है और S भी है। अच्छा, ये mc स्क्वायर्ड क्या है? रेस्ट मास ऑफ द इलेक्ट्रॉन। रेस्ट मास ऑफ द इलेक्ट्रॉन कितना होता है? 0.5 वाट किलोग्राम MeV, 0.5 MeV। En कितना होता है? सबसे बड़ा En कौन सा है? ग्राउंड स्टेट कितना है? 13 इलेक्ट्रॉन वोल्ट। उसका स्क्वायर कितना होगा? 13 इलेक्ट्रॉन वोल्ट स्क्वायर। So this is MeV, this is 10 to the 6, and that's 1 of the order of, let's say, 10 to the 2. So this whole number is of the order 10 to the minus 4. So you can use perturbation theory. ठीक है? So जब आप इलेक्ट्रॉन की, जब आप हाइड्रोजन एटम का स्पेक्ट्रम देखते हैं तो आपको कुछ लाइंस थिकन्ड नजर आती हैं। जब आपको बहुत गौर से देखते हैं आपको पता लगता है कि असल में वो एक से ज्यादा लाइन है और वो स्प्लिट हुई है। वो किस वजह से स्प्लिट हुई है? अपनी L और S वैल्यू की वजह से स्प्लिट हुई है। You don't have to do anything else. Okay? Homework. Reading assignment. Human effect. So ये तो था कि आपके पास इलेक्ट्रॉन जो है वो प्रोटॉन की मैग्नेटिक फील्ड एक्सपीरियंस करता है। अगर आप उसको एक्सटर्नल मैग्नेटिक फील्ड में रखें, उसको उठाएं और एक्सटर्नल मैग्नेटिक फील्ड में रखें तो फिर क्या होगा? ठीक है, that's the matter, and we have done that in detail, so we can just read that, and that will be part of our grand final exam. This Sara. भैया बचिया, तुम ये तीसरी दफा पढ़ रही हो, हैं? तुम्हें अभी ये ज़्यादा लग रहा है? हैं? जी करवाया था मैंने क्लास में, और उस वक्त मैंने 3 क्लासों में करवाया। लेकिन ये आप लोग बहुत डिटेल में कर चुके हैं, इसलिए मैंने इसको आखिर में रखा था कि अगर आप ये ना भी करवा सकें तो इतना इशू नहीं होना चाहिए। नहीं, जो ज़्यादा इशू वाले टॉपिक्स पे, एक्सेप्ट फॉर मे बी आई वाज थिंकिंग टुडे दैट वी शुड हैव डन विद द आइडेंटिकल पार्टिकल्स, लेकिन वो भी इतना मुश्किल नहीं है। So 3-dimensional Schrödinger equation, spherically symmetric problems, addition of angular momentum. That's usually what's lacking in a traditional quantum mechanics course. ये ज़्यादा अच्छी तरह से समझ गए। Anyhow, if there are no questions.
कैमरा कहाँ से लगता है?